It is 3 o'clock here in Europe. I'm not sure if there are lots of people from other sides of the world. This is a session about mutexes, and actually it's I let Gianni put in a mini session, and as I will come back to it later, with modern current databases, which are databases of version 12 and higher, the likeliness of mutexes actually being a problem is really, really close. So if you have a really short attention span, you can cut off now. The mutex is probably not your problem. If you are willing to learn a little bit more, you can continue on listening, but that is the shortest version of the presentation that I can do. Okay, about me. My name is Frits Hoogland. I'm Dutch. I'm a principal consultant with the Accenture Architect Group. I like very hard problems. I spent quite an amount of time with the Oracle database and investigating the Oracle database. I like the combination of hardware, networking, operating systems. Actually, cloud is just exactly a combination of that. So I still see cloud as running stuff somewhere else with all the implication that it had, like Camille was talking about. This is actually that I warned for inside our company to a lot of people, because if you don't get that almost by definition your database is at a different networking segment than your application server, it must mean that your network distance is higher. I also like automation and infrastructure automation, so not so much the programming part, but installing Oracle, for example, and I have a suite which can install the Oracle database automatically and just search on GitHub for Vagrant Builder. There's a tool set that I built for that, which is free to use. I have done some book reviewing, and I even wrote a few chapters for Oracle Expert Exadata. I'm a member of the Oak Table. If you've got any questions or follow-up questions, or are interested to dive into this deeper, or have any comments of any nature, please get it to me via Twitter or via email. And I've got a blog, and a lot of this stuff is on my blog, and I will make this presentation available on my blog. Like Camille's talk, I should say, what you should be aware of, this presentation has nothing to do with daily operations. This is research, and it has to do with a single specific mechanism, which is the database mutex. So if you do not like detailed information or etc., this is just not for you. Then it doesn't make sense to follow this. But if you like to get a fundamental understanding of how the database actually works, which I think is the only way to do decent troubleshooting and performance tuning, or if you just want to learn how stuff works, and a lot of stuff deep down has to do a lot of work to do seemingly simple things for you as a user, then this talk is for you. This talk works best if you have some knowledge about general concepts, especially on spin locks in general, and a mutex is a spin lock. I've done this investigation in Oracle 18.4. If you would like to ask why 18.4, well, that was the most recent version when I started investigating this topic, actually. So I have been investigating this for quite a long time, and all I can say is, if you want to build a complete picture of stuff for which you have to really dig deep for and for which there is not really a lot of documentation, it takes time. It simply takes time. Any of these mechanisms can change because they're internal. They can change without any warning from Oracle or any documentation surrounding it. However, the general tendency is that at least the principle of the mechanics does not change that much. So it still means that if you assume something, you have to do or perform a little test to make sure that what you're saying or think is happening is actually still happening. Okay, and now to the actual gist of the presentation. What is a mutex? Well, a mutex is a memory structure, and the purpose of that memory structure is to manage concurrency. And actually, this is 100% exactly what Oracle database latches have been doing for a long time in the Oracle database. An Oracle database mutex is something different than an operating system mutex, although both apply the same principle of managing concurrency. Oracle database mutexes, Oracle database latches, and operating system mutexes are all implementation of spin locks. So, and a spin lock means that if a process wants to get to a shared resource, it looks at a certain memory area, and if the memory area is not compatible with what you want to do, it reads it again. And it does that.
Quickly, Frits, can I just ask you, are you using a wired microphone or so? Because we have some people saying that there's an echo in your voice.
Okay, let me try to... Let me see if I can switch microphones then, but then I have to...
Hello, is this better? Is this different?
For me, it's fine. We have people saying that it's fine. Okay, yeah, but now it's perfect. Okay, much better, much better. Okay, okay.
Okay.
Thanks,
yeah.
thanks, people. Everybody.
Yep. Okay. So where was I? The principle of a spin lock, which are the Oracle database mutex and Oracle database latch, and an operating system spin lock, which can be an operating system mutex, which is something entirely different. The basic principle is all the same, and the idea and the assumption is that the spin locks are only ever briefly held, and therefore the spinning should take a very short amount of time. Let's see. Mutexes in the Oracle database, and I was actually quite surprised when I did research about this, that they have been implemented since Oracle 10.2. I was not aware of that. What one thing I noticed, and one thing I actually have tried troubleshooting in the past, is up until approximately version 11.203, there was no backup mechanism for Oracle mutexes. And if you like to know more about it, you can see a bug. Is there something else? I see something blinking. Please, if there is something which I should change, then please make it known, but otherwise I'll take questions at the end. If you'd like to know more about the implementation of the backup mechanism, look for the bug number, which is in the presentation. I will make the presentation available after this talk. And up until approximately 11.203, there was no backup mechanism like there is for latches. And most of you probably know for latches, the first backup mechanism is sleeping. So it spins a couple of times, then it sleeps, and then it spins a couple of times. And after repeating that sequence, it goes to sleep on a semaphore. Not having a backup mechanism at that time could lead to a process spinning for a mutex. And because spinning for a mutex is reading a piece of memory, if it's found to be incompatible with what the process wants to do, it simply reads it again. So if you are doing that, then it will occupy a CPU entirely. And if you have a system which is pretty much maxed out on CPU, so processes are churning, are doing a big of work, holding such a mutex, and a new process comes and tries to obtain it and then starts spinning for the CPU, this new process gets a higher priority because it's a newer process, and then has the ability to push processes away, which potentially could be the process which is actually holding the mutex you're spinning for, and therefore it can essentially lead to a death spiral for the instance. So this is not a good thing to do. Even without mutexes, if your load exceeds your actual CPU capacity, it takes away the possibility for userland processes to schedule and execute actions at will, which means the order of things to happen gets random. And that means that the previous description of a situation which I just told you could happen. So the takeaway message here is, if you want your database to perform and to perform in a stable way, it should not get close to the actual CPU capacity. And one way of achieving that, if you cannot really control the amount of processes which get active, is to use the database resource manager to manage it. Since the base release of 11.204, mutexes have a backup mechanism, and actually, and that is what you will see in this bug report, which I shown earlier. There are different schemes, of which the default scheme is 2, which is in this underscore mutex underscore wait underscore scheme, etc. So it has these specifics. This prevents spinning mutexes from consuming a full CPU. And since it sleeps on a semaphore, if it totally goes to sleep, and it's using the Oracle database post-wait mechanism for it, it can also get woken whenever the resource becomes available, whenever the mutex becomes available. Since mutexes do a lot of what latches do, this is a slide about latches. Latches are different, and the reason for the existence of this slide is to point out the differences for these. Latches, there are 2 kinds of latches, which are parent and child latches. And parent latches, the memory for the latch is allocated in a fixed SGA at a consistent address. So inside the database, Oracle can simply code the address for the parent latch, and it can jump to it directly. It doesn't need to look anything up. What I've seen quite frequently is that parent latches have an array of pointers to child latches, because child latches are, the number is dynamic. Most of the number of child latches are, as far as I know, derived from the instance parameters, and the child latches are allocated in a shared pool. So that means they are essentially at a random address, at a random place in the shared pool. And therefore, in most cases that I've seen, a pointer to the first latch is stored with the parent latch. Because of the nature of this addressing, it's that at all times the number and the location of latches is known by the Oracle database instance, and therefore it's quite easy to keep track of the latches and the usage of latches of every distinct latch. One of the things which I see is really different from a mutex is that a latch, not always, but quite typically, protect multiple independent resources. And one of the resources, and one of these resources that I'm talking about as an example, is the CAS buffer chains latch. The CAS buffer chains latch protects the hash buckets of the buffer cache. So, and a latch typically protects a number of buckets, and each bucket contains a chain of actual buffers. So if one gets busy, another bucket can be affected because it's protected by the same latch. And I think that is the whole aim of what a mutex tries to circumvent. Because a mutex is really different in the sense that it's dynamically created inside and as part of an object that it protects, such as a library cache hash bucket, a library cache handle, a row cache parent, etc. This also means that a mutex is removed if this object is removed. And one of the things, well, which can be removed, obviously hash buckets cannot be removed, but a library cache handle and a row cache parent can. Also, probably to make the overhead for mutexes as low as possible, there is no central registration of individual mutex existence and statistics. This is a true key difference from latches. And mutexes are implemented at very specific code locations. One is KKS, that is shared cursors, and there the mutexes can be found in the parent's heap 0. It's KGL, that's the library cache, and that's the library cache hash table and the library cache handles. KQR, that is the row cache, and that's row cache concurrency. And one thing I simply did not investigate because that is something entirely different. That is KDLW, and that is kernel data lob write. And I see mutexes there too, but I've simply not looked into these, nor ever came across mutex issues with these. If you want to look at views, at the information which the instance is able to give you, there's mutex sleep, which essentially, well, to me, for myself, I see it as an equivalent of a VDOLA system event, and it just keeps track of actual sleeps. So this is filled whenever there is a sleep for a mutex, and that is per sleep location. Wait time is in milliseconds. And there is mutex sleep history, and this one is quite interesting because whenever a process needs to sleep for obtaining a mutex, it will put an entry in this array. And then there are two more historical views, which is DBA hist mutex sleep, which is an AWR snapshot of VDOLA mutex sleep, and there is the CDB equivalent. Now let's dive a little deeper, and that is AOL and UOLs, which are mutex state objects. And for the persons who joined Tanel's session about state objects, a state object is very important to Oracle because it's a second mechanism of keeping track of something that's executed in case a process gets killed. So there is, it is known what resources are taken. So whenever a process is going to be accessing a mutex, a help structure as a state object is going to be created up front. And this structure is known as a UOL. That's a U. I've never seen what the abbreviation means, but I translate it for myself as user operation log. And the UOL contains AOLs, which are atomic operation log entries. And the abbreviation atomic operation log entry is actually documented in my Oracle support. And the change or the intention for a change to a mutex is written to a specific operation log entry. For example, on the left side, you'll see KGL UOL, that's the first line. Then you see KGX atomic operation log. Then on the next line, you see mutex and then a mutex address. And then after OPER, you see EXCL6. Well, number 6 is the number for an exclusive get for a mutex. If you then move over to the right side, you see essentially the same. However, the KGX atomic operation log has a different address because this belongs to a session. And the mutex is exactly the same. But what you see at OPER is get EXCL number 5. So it has the intention to exclusively get this mutex. Well, and as you can see on the left side, another process is actually holding it. You can even dig a little deeper from this UOL dump, and that is it's a library cache mutex. It's obtained from location 62. That's after the WHR where, and 62 actually is a mutex. An hash table get, but that's easy to obtain from the location, which I see later on. And SLP means sleep, so you can see that this process is sleeping. And if you look back to the other one, you see SLP 0, so that process didn't sleep for getting this mutex. A URL is created using the C function KGL get session URL, and it is located in a shared pool area. So it's not allocated. The URL is not allocated in the PGA, which would be my first guess, but it has a very specific reason for not being allocated in the PGA. But the session state, so the URL, is allocated in a shared pool area, which is identified by the name KKSSP caret and then the SID of the process. Inside KKSSP, a URL is allocated in a subpool called KGLSS, which probably is kernel generic library cache session state. KKSSP probably means kernel compiles session state pages. And an important thing is multiple URLs can be allocated at the same time in the KKSSP shared pool structure for the session. And they are dependent upon the mutex change occasion and the type. So there is not a general session scoped URL structure, but there are multiple URLs for specific use. An AOL entry, well, not all the time, but most of the time I see an AOL entry in the URL being allocated or initialized using the C function KGL AOL init. The function of the AOL is to have log-like metadata, for example, to make cleaning them up in case of a session crash possible. And this is the exact reason that the KKSSP memory is in the shared pool and not in PGA. Because the OL is a state object, and one of the functions for a state object is to give another session, in the case of mutexes PMON, to clean up orphaned resources if a session actually crashed. Because if your session would crash whilst holding a mutex, otherwise this mutex would always be held. And using the state object, the URL, PMON can read what mutexes it was holding, and if it knows the process is dead, it can free these resources. The KKSSP area is also documented to contain the state objects of pins and library cache logs. And if you like to verify that, these are the bug numbers and my Oracle support notes, which actually describe this. There is no dump or event that I'm aware of which actually can give you a dump of all the mutexes. And the reason for the mutexes is the instance it does not know where these are. You encounter them if you want to access an object, but there is no central registry of all the mutexes which are there. However, if you find problems, you can dump the URLs that the session has allocated and look at these. And one of them is, if you want to know all of the mutex states, you can perform a system state dump, which will dump all the URLs of all the sessions. And so in that case, you can know the state of all the mutexes it is holding. And if you want to know it of a single process, you can execute a process state dump. And the actual command to do so is here in the presentation. And the My Oracle support note tells you a little bit more about reading a system state dump. If you encounter a library cache mutex wait, which is the library cache bucket mutex X wait event, it has the three parameters which it shows you. And these are the sequels which you can execute to actually obtain information about what the requesting session is trying to get it for. So it does not tell you what the session holding it is using it for, but it will tell you what the requesting session wants to do with it. Because the first one for library cat bucket mutexes is the bucket number. And using the bucket number, you can obtain the parent and all the children as part of the parent and the addresses using this SQL with P1. However, if this bucket is held and you try to specifically obtain information about this bucket, it will block too. So you have to be a little careful and not blindly execute this in a production environment. For the blocking SID is kind of hidden in the high order bits of the blocking SID number, which makes it not really obvious to read because it will just show us a really big number. And using this bit end, which is actually just a division by the low order 32 bits, that's power 2 to the 32nd power, it will just shift the bits and then do the bit end on the bits which are left after that. So that is what is bit end division by power trick actually is doing. It is dividing and then setting a bitmap. So that is what it is doing. And then the location from external mutex sleep is can be obtained in this way. This is a wait for an exclusive get of the mutex specific to the library cache bucket. Anytime a bucket is read to find the library cache handle, this mutex is taken exclusively. And it does so for two reasons. First of all, there is a counter in the bucket mutex to be able to count the usage. And in order to do that in a consistent way, it needs to get it exclusively. I don't think that, well, you need to really excessively oversubscribe on memory to cause swapping or CPU to make this, to influence this in a really bad way. But the second one is more interesting, and I put it down here. It's quite an internal description, but it's just to get awareness of why you could be waiting for this wait event and be waiting for the bucket mutex. And that is, if a parent handle needs to be created, it needs to have unique access to the bucket because it needs to add the parent to the bucket chain. So it obtains the bucket mutex exclusively. After that, it calls the function to obtain or create the parent handle, which is KGL HDGN. If KGL HDGN does not find the handle to be present, it will call KGL HDAL to allocate the handle. This function needs to find some space to put a handle in, handle on. That is quite obvious. But in order to allocate a space, it needs to obtain the shared poollets to get to uniquely get access to the free list to allocate some memory. So that means if your instance is short on memory, other processes might be trying to to allocate a shared pool memory, and it might be hard to actually find a free chunk. And in these kind of cases, there can be some time which is spent in this wait event, which is actually memory shortage. But because allocating memory for the parent handle is spent whilst this mutex is taken, you can find this this wait event. Then library cache mutex X. If the parent handle does exist, then first the bucket mutex is obtained and left, and then in order to obtain the handle in a unique mode, the library cache mutex X wait event is used. These are the sequels which you can use to obtain information about parameter 1, 2, and 3. The same the same warning is here. if you see it and if you see this weight and you try to obtain the handle using the parameter using P1 from X dollar $KGL_OB, then this will probably block too, because it will try to read the handle. So be aware that this might, because you're looking at the same object in the database which is blocking, so you will be blocked too. Why would it wait for library cache mutex X? Well, it shouldn't 9 out of 10 times. However, anytime anything in the parent handle, in the parent library cache handle needs changing, and that is for obtaining a log, for obtaining a pin, for any statistics, so any usage will access the handles to change stuff. And that is only done very, very briefly, but it's done a lot of time. It will use this mutex. So the first one is the counter. Well, as I've said previously, for the counter for the bucket, I don't see a problem there. However, after the handle is created, if heaps needs to be created as part of this library cache object, it will allocate the heaps holding the library cache mutex X mutex. And therefore, the same applies as for the same principle applies as for the library cache bucket mutex. You can see processes waiting for library cache mutex X if there actually is shared pool shortage, because it will hold the mutex whilst it is doing the allocation. And if you are, for some reason, have so much problems that it will generate a backtrace or a stack trace, you will see KGL OBAL. So that's not K global, but it's KGL, so kernel generic library cache, OB for object, and then AL for allocation. And another thing it does, because the heaps tend to be quite much bigger than the handle, it might need multiple chunks of memories. And if memory has been previously used, it will the process itself needs to free the chunks it wants to allocate itself. And in order to free the chunks, it needs to read the chunk headers and actually use the code for which for the reason of which the chunk was allocated to free it. So you might see, if you get a backtrace, you might see, for example, dictionary cache code, because it's trying to deallocate a chunk of row cache, dictionary cache memory, in order for a heap 0 of the library cache to be allocated. So the short version is shortage of shared pool memory could cause this wait event, this mutex, to be taken. Then library cache dependency mutex. There is one mutex which is truly independent for every child cursor, and that is the dependency mutex. All the children and the parent handle share the same mutex for using it. However, the dependency mutex is unique per child. I can see why this is the case, because some objects like sysdual, for example, could potentially have a lot of dependencies. So general usage is not disturbed by this for access, because the dependencies are done via their own mutex. However, I cannot come to any scenario where I can explicitly, in a normal use case scenario, obtain the dependency mutex. And the reason for telling this is, if you look at the descriptions in $3 event name for parameter 1, 2, and 3, you see that for all the mutex related ones, it says for parameter 1, for most of them, it says IDN. But as hopefully you just gotten from what I just described, for library cache bucket mutex X, IDN is actually the bucket number. And for library cache mutex X, IDN is actually the library cache hash value. So these are different. So I simply don't know what P1, 2, and 3 for the dependency mutex X are. Also, the memory for the dependencies, for the dependency tables of the objects is gotten outside of the mutex get. So it is not memory allocation of the shared pool is not actually part of the weight for this mutex. Then cursor. For cursor, you can see the amount of references in case of a shared mutex get with P2. And you can see the actual eventual blocking SID. And it uses the hash value in P1, just like the library cache ones did. However, there are way more mutexes for a cursor than there are for the library cache entries. There is a parent mutex that I can see, a hash table mutex, and the hash table in the parents heap 0 is the actual list of child cursors. And there is a cursor for the pinning, and which is in the parent heap. So all the, as far as I can see, all the cursor mutexes of all the children are actually in the parents heap 0. The most common weight, which you probably will see, and this is actually not a mutex weight, but a cursor state weight, and that is cursor pin S weight on X. And what this means is a session, your session needs introduces a new SQL, and it looks up the parent handle, and it actually finds an already allocated parent handle for the SQL it tries to execute. So then the next thing to do is trying to find a suitable child for execution. The way to do that is by scanning the child list, which is done from the most recent child to the oldest, so in reverse order of creation, and it needs to pin every distinct child for a cursor in order to find a suitable child. So what this weight means is that your session tries to pin a child in shared mode, but it can't because another session currently has the child you try to investigate is holding it pinned in X mode, which is exclusive mode. This typically happens when a child is being created, and because a child being created is typically the newest, well, it can only be the newest one. This will be the first one that you run into, which is also quite obvious because the newest one probably shows the uses the latest state of how the data looks like. So that is probably the best one to choose. So it totally makes sense. If you look at location ID P3, you'll find cursor pin KKSLCE, KKS CHLPIN2, which probably just means KKS, so that's kernel compiles shared cursors log child entry for LCE. Then another one, row cache mutex. When I look at the location naming of row cache mutexes, it tells me that the row cache mutex implementation is done by a totally different team because it looks totally different. If you look at a P1, forgetting for the row cache mutex weight, it says select distinct, and that's not a typo, but some of the caches, some of the row caches have multiple entries with the same cache ID. So in order to just get a list of the cache IDs, I put in distinct. And P3 is not used here. So this one is way simpler. It also is not able to tell you whether it's actually blocking for the mutex, for the bucket mutex of a cache, or the parent object mutex for a cache. If a row cache parent object does not exist, it needs to be allocated before the row can be read into the cache. So the same applies here. The allocation of the parent memory is done whilst holding the row cache parent object mutex. So shortness in a shared pool memory can actually give you row cache mutex weights. After the mutex of the parent object is taken, the parent enqueue is set and the mutex is freed. If a row cache entry needs to be read, so if there is a row cache miss and it needs to fill it, it will completely recursively execute SQL to insert it into it. But that is done using the wait event row cache log and not row cache mutex. So still row cache mutex should be not frequently seen if you have if your shared pool is too little. Other sessions, like I described before, could free up memory at a fairly high rate, which means your row cache it will be automatically shrinking. And then when you need to use the row cache, it can have the need to allocate the memory again and then put stuff in the cache recursively too. Some of this row cache gathering and this information is shown with event 10.222. A lot of the documentation says that mutexes are a way simpler mechanism than latches. I'm not sure if I agree. If you go into if you attach GDB to a random Oracle database session and you execute the commands which have GDB in front of them, you can scroll through the actual different states, the different opcodes for mutex states. And as you can see, there are, together with none, there are 19 states that the mutex can have. So it's not only a shared get and an exclusive get, but there is also something called examination mode and a long exclusive get, etc. Well, I'm not going to dig into this too much, but if you have backtraces, this is a description and what some of the parameters mean of the C functions. So, well, if you use a pin debug trace or if you use a debugger, then this can be of help. If that is way too low level, then this will probably not be of help, but these are the individual C functions which the database uses to manipulate and use mutexes. And this is a second screen. I do not know exactly what all the individual functions mean. For example, there is KGL mutex not held, which is a really short function, and I don't understand it because just prior to that, KGL mutex held is called, which mutex not held seems to me the inverse of KGLS is mutex held. So sometimes it's not really obvious what the functions are doing. So now that I talked you through, and hopefully you you stayed because you were still interested, despite me saying that it's probably not an issue, your mutexes. How much are mutexes really being used? Is it seldom or not? Well, let's go the Camille route for a bit and actually let's dig into, I hope everybody can see my screen. On the left side, I'm just logged into the Oracle database and I'm setting up a really simple SQL, which is select 8 from Jewel. On the other side, I look up the ID, the PID of this process. And I, damn it. I execute a number of breakpoints. And these breakpoints are all the KGX related function, which is KGL exclusive, etc. These are all the functions that I could find. And all I do is I print the instruction pointer, which will show the instruction pointer location, which will tell the actual function. And what the idea is that this gives an idea how much mutexes are actually used, because as I also said, they are used in really specific cases, which is shared cursor handling, row cache handling, library cache handling, and lob rights, and lob rights is not what I'm going to do. Now I'm continuing here. Every time the instruction pointer and the instruction pointer name is put on the screen, it will also number them. So this way you can get an idea how much mutexes or mutex manipulation a really simple SQL is doing. So that's 221. What is nice to know is if you, this is the first execution, so that's 220 approximately. If you execute this again, then the number gets lesser. And why is this number getting lesser? Well, the first one was a hard pass, so it needed to do a lot of work. The second one is a soft pass, so it needed to do less work, and that's 220, 250, so that's approximately, very roughly 30 instead of 220. If I execute it again, it's 250, 270, so that's 20. And if I then execute it a fourth time, I only get 4. So it shows you that, well, one of the things which this shows is not all soft passes are equal, but the main aim for this is to show you that it is doing a lot of mutex gets. So now let's get back to my screen. Hopefully this gave you an idea that it's really, I think it's quite important to understand that they are there. So the conclusion, in recent versions, and recent versions is 11.204 and higher, so roughly 12 and higher, I have not encountered excessive mutex gets issues. Sorry, I have not encountered excessive mutex issues. That's what I said at the start, right? You should not see a lot of mutex issues. In any normal circumstances, mutex weights mean concurrency. Why do I say normal? Well, if there is leakage of a mutex state, then obviously it will keep it locked forever, but it's not really concurrency, it's just leaking of pins or leaking of mutex gets. Mutex issues are really more likely to occur when an environment forces non-SQL execution. And as I put in, this is fancy speak for if you are overscribing your CPU and processes are forced to go to sleep by the operating system because there are more processes wanting to sleep than there are actual CPUs to run on, then there is a chance that the process holding the mutex is forced to sleep whilst you are spinning for it. If you want to understand if this is happening at in your case, I say total AAS, and total AAS means it's the average active sessions of all the databases running on a machine. If that's bigger than roughly all the CPU cores that you have available, you're oversubscribing. So I've seen this a couple of times, 100% CPU usage being the optimal usage of machine and CPU. This is 100% bullshit and not true. Most mutexes issues that I encounter eventually turned out to be CPU oversubscription and therefore amplifying mutex weights. So that is the session that I had prepared. Are there any questions?
Yes, you can find the 2 questions at the moment in the Q&A window, if you can see it somewhere in your Zoom.
Yeah, I see Q&A and number 2, but I do not seem to be able to get it to the front. Is there any way to do that? It's now 3.
Yeah, I mean, it's supposed to be, but it's probably like behind another screen or something. So the first question is, was the third execution, second soft parse of select 8 from dual, even less intensive because the cursor got session cached?
The session, a second execution of a new, the first one obviously need to be hard passed, and I just started, well, I did not just start a database. So select 8 from Jewel might have been in the shared pool or not. And actually, when I just started the database to rehearse for this, I got over 1,000 mutex gets. So probably this wasn't a hard pass. The second one, a second execution need to do some execution, but only if you see the 4 mutex gets, then it is in the session cursor cache. So it's only if you, with these 4, I am quite sure that it's in the session cache, and it wasn't up front. I just started the session. So it wasn't in the session cache before that.
Good. So another question is, the script that you're running in GDB, will it be shared after the session, or is it somewhere online on your website, blog, or something?
That's a good idea. I will share the GDB script that I used in on my blog. I will do that.
Yeah, perfect. Thank you very much. Another question: are mutexes owned at the CDB level or PDB level in a multi-tenant environment?
From the perspective, a mutex is held on the PDB level. No, for the database, essentially, it's just a mutex, so it's just a memory location. So logically said, it's independent of a PDB. And now that I'm thinking about it, the library cache is not divided per PDB. So in essence, it's not a PDB level thing, but a CDB level thing. So it's a global, it's an instance-wide phenomenon. So the important takeaway, and I should test it, but what I think, if one session holds a mutex in one PDB and you're executing 100% the same SQL, it will hash to the same value, and thus you will be waiting for the mutex of another PDB. And that is probably the reason for this question. So I think it's an instance-wide thing and not a PDB level thing, unless library cache entries are segmented by PDB, which I am reasonably sure is not happening.
Okay, so 2 more questions. What is AAS here?
Sorry, what is A?
AAS, 3 letters, AAS.
AAS, that is part of active session history, and that it means average active sessions. And average active sessions, you should look for the old presentations of Graham Wood, who now retired, and John Breckenridge, who's now with Oracle again, has presentations about it. And essentially, this figure tells you the average amount of active sessions. So, which means the average amount of processes which are active in your instance.
Okay, so the next question: at which point do we consider a system being oversubscribed?
A system is oversubscribed very simply, and you should actually look at the system level and not at the database level. Whenever the amount of processes that wants to be runnable is higher than the amount of cores you've got in your database. It depends a little on the architecture of the CPU and the type of CPU, etc. But the rough rule of thumb is truly active sessions at a certain point in time, or sessions willing to be active, and the amount of CPU cores that you've got. And the essence of it, if there is more processes that want to be actively doing something than you have on units that can actually make processes execute, then the operating system, if you do not use a database resource manager, needs to make a choice on what to run. And that is the essence. And because the operating system has no concept of what is important or what is holding an important resource, it will do it just on the assumption of the cost it puts against it. And that's what I said. If a process is churning for a very long time, holding the mutex because it's doing batch processing or whatever, and then a new process comes and it tries to obtain it, the newer process is newer, therefore it will get more priority and it will push off the CPU. It will push off the older process of the CPU because it's been running longer. So the operating system trying to apply fairness will make the new process have more priority, whilst the old process potentially could have this mutex, could be holding this mutex. And that is because, again, the operating system does not understand what is of importance and what isn't.
Okay, so this one is done as well. Now there is one question left, which I'm not really sure how to, what they are really asking. AAS larger than number of CPUs. Please explain how to draw this rationale. Not really sure how to read it or what it exactly means.
It's essentially what I said with the previous question about AAS. If you look at the operating system level of things, and you look at the amount of processes that are willing to be active in total, so that also includes non-Oracle processes, because it's an operating system scope thing, and the operating system is limited by the amount of virtual CPUs that it sees. And the amount of cores is what you actually got that is actually executing. So anytime there is more willing to run processes than you can, then the hardware can actually run for you. Something has to be pushed to the side somewhere. And AES is just an aid. It's terminology which was invented by, as far as I know, by Graham Woods and John Breckenridge and others at Oracle, to essentially just tell you how many processes in Oracle are willing to be active. That is, so it boils down to the previous answer.
Okay. There is just a last one, what they ask you to write actually in the chat. If you can write the full name of these two gentlemen, Mood and the other one. You just say the names of the two guys. They ask you that you can write them in the chat.
Yeah, then I'll stop screen sharing and then hopefully I can see the Q&A too. So
there are a few other questions jumping in, so you can answer them by writing, so we can move on to the last session of the day. Thank you very much, Frits.
Yep, thank you.